And we're on.
Okay, well, welcome back. Gavin and I will today be discussing some of the material from Dawkins's chapter 5 and 6. Chapter 5 was The Power in the Archives. Chapter 6 is Origins and Miracles. A few things we wanted to point out. First, I wanted to note that this week we're asking you to watch today is the 21st, so we're asking you to watch the first two parts of a series that was written, produced, and narrated by your author, by your book author, Richard Dawkins. And it's a series that aired on public television in the United Kingdom initially. It's called The Genius of Charles Darwin. And this series, among other things, gives you really an excellent overview of evolution by natural selection, of the history of evolutionary thinking with a special focus, of course, on Charles Darwin. And I think does a really nice job of bringing to life a lot of what we're talking about in these first 5 or 6 chapters of The Blind Watchmaker. I do believe he will make reference specifically to The Blind Watchmaker, so he'll tie it directly into the sort of the broad theme of the book. And of course, Dawkins talks at length about natural selection. He also interviews several colleagues and researchers in the field. And like many of his documentaries that are aired on BBC, on the public television in the United Kingdom, it's extremely well done, sort of high level, camera work and cinematography. It's really quite nice. So the first 2 episodes, which we're asking you to see, each one is about 50 minutes. The first one is called Life, Darwin, and Everything. The second episode is called The Fifth Ape. That would be humans. And then next week, among other episodes, we'll ask you to check out the final part of this series, which is called God Strikes Back. And it sort of assesses or addresses the potential conflicts between science and religion, and specifically between natural selection or evolution and religion in the form of special creation. So you hear lots about Darwin, lots about evolution, lots about natural selection, and lots about the blind watchmaker, that sort of perspective on life. So we certainly hope that you guys will find those videos useful. Just for this week, then, just to be clear, it's just parts 1 and 2. Okay, it's not even 2 hours. Next week, it's part 3, and then we'll ask you to see one of the parts from the PBS Evolution series, and we'll talk more about that next time. So before we talk about the chapter, Gavin had a couple of, he wanted to address a question that I think came up several times was it in the discussion questions or was it in the reaction papers?
It was in the discussion questions.
Okay, go ahead.
Yeah, so I had quite a few people not really sure what Dawkins meant when he was referring to the X, when he was talking about the evolution of the eye, and he says to imagine an X, some X that's sufficiently close to the modern human eye, such that it could occur within a single step of mutation, natural selection, a single generation.
Right.
And that's basically all the X is. And whatever you have to imagine, it's like basically Dawkins's way of saying, what is the smallest step away from the modern human eye that you can sort of make? What's the, well, smallest or largest, or I guess what he's saying is the most reasonable jump you can make from our modern human eye to the next step back in evolution. And that could be a modern human eye with one fewer photoreceptor than what
Right.
humans are typically born with. It could be that small. It could even be a modern human eye with a slightly less efficient photoreceptor or a slightly shorter photoreceptor. Just something, or maybe even a slightly thinner or smaller lens.
Right.
Something that's so small that you can imagine a mutation, a random mutation, occurring like as a single step from that, one single step back to the modern current eye. And
Right.
the whole point of him doing that is basically to show how gradually natural selection does happen in order to persuade you that, there are no big leaps or bounds happening here. It's all within sort of a reasonable uh, parameters.
That sounds good. So bottom line is, I think that's a nice summary of what Dawkins is doing there. And just to be super clear, in case this was the question that was being asked, X is just a stand-in for whatever variable you happen to be talking about. So in this example with the eye, X was whatever came right before the modern human eye, as Gavin just said. But if you were talking about, if we were talking about the heart, well, then X would be whatever would be one step back or one tiny change in a previous generation. So it's almost like it's one step removed from the modern human heart. So X is just a stand-in for whatever variable you happen to be talking about.
Right. Yeah. And another sort of related to this question, another one I did get and wanted to address because I think it's important. A lot last week is a few people, not as many people asking about the X, but asking, being a little hung up on the details of how 5% of something can still be beneficial, or how 1% of, an adaptation can be beneficial to an animal. And
Right.
I had a personal example that I thought was sort of funny and might help some people conceptualize it. So I was at band practice, right? And we are, practicing in a basement in Detroit, or outside of Detroit. And we saw this spider crawl across the basement floor. And I said, do you think the spider has sustained any hearing damage from living in this basement, to my bandmates? And then that kind of got us talking. And one of them ended up looking it up because we were curious about how spiders hear things. And they were pretty sure spiders don't have eardrums. I had no idea because I have never looked it up before. And they looked it up, and spiders don't really have hearing. But what they do have is they have hairs on their bodies, and snakes, similarly, don't have hearing or eardrums, but they do sense vibrations. And so I learned that, but I kind of thought that really seems like just a very prototype version of hearing. So similar to Dawkins' example of a patch of photoreceptive light or photoreceptive skin cells being a precursor to an eye, you can see that there are real animals with sort of a prototype version of hearing that's just sensing vibrations, which is
Sure.
really all your ear or your eardrum or the mechanics in your ear, like the hammer, anvil, stirrup, do. Is there are more complicated versions of interpreting smaller variations in pitch than simple vibrations like snakes and spiders are able to do.
Right.
So if it's difficult for you to imagine that with the eye, you can look at real animals and use hearing or ears as a different sort of example to see how 5% of something or 1% of an adaptation can very much be beneficial to different animals. So
Sure. Yeah. But it may not be. Yeah, that's a great example, Gavin. And it may not be that it's, when you think about an eye, and when he uses terms like 5% of an eye, I mean, what you don't want to do is try to imagine literally a carved out 5% of an already formed eye, because then that would just be, just a little massive tissue. I mean, that wouldn't really, that's taking the metaphor, too literally.
right.
So the idea is 5% performance, or 5%, better or worse in, ability to detect vibrations, for example, or ability to detect light, rather than, it's not as if 5%, of what we're calling the equivalent of hearing in spiders doesn't mean, every 5, out of 100 hairs on the spider's body. Anyways, the point is, I think that's a great example, and it's a good way to sort of recast, some of the examples that he's giving in terms of the evolution over time gradually of the performance of, or the functions of these various adaptations. What matters and what is crucial is that not only could there be the gradualistic evolution of what we, in hindsight, can recognize as a human eye, not only could it have evolved gradually, but it must have evolved gradually. Given that, as we talked about in one of the other chapters, one of them, I think the most recent chapter, Making Tracks for Animal Space, large leaps across genetic space almost always are lethal. And so, the tiniest steps in genetic space have, at best, a 50% chance of improving things.
Right.
And so it must be tiny steps. And all that matters is that that step leads the trait to be more functional or better performing than alternative designs. It doesn't have to be a step from light-sensitive cell to a fully functioning, complex human eye. In fact, it's not going to be that kind of a step. So, all right, very good. Thanks, Gavin.
Yep.
Okay, so he's talking about the power in the archives. So a couple of ways we could do this. He does define power a bit further in the chapter. I wanted to just jump to it real quick and see if it helps to sort of situate this chapter. So on page 183, he is, let me see if I can find a good place to sort of jump onto this. He's making the case that, what is it that distinguishes life? What is it that, what is the distinguishing feature of what we might call life? And this is something that philosophers and scholars have been debating, for centuries, often sort of in a misguided way. Let me see. He argues that, at one point at the top page 183, he's making reference to possibly to a Bible verse. Yes, Ezekiel's dry bones. So he says, what is the vital ingredient that a dead planet like the early Earth must have if it is to have a chance of eventually coming alive, as our planet did? It is not breath, not wind, not any kind of elixir or potion. It is not a substance at all. It is a property, the property of self-replication. This is the basic ingredient of cumulative selection. There must somehow, as a consequence of the ordinary laws of physics, come into being self-copying entities, or, as I shall call them, replicators. Okay, he goes on to say, in modern life, this role is filled almost entirely by DNA molecules, about which you hear quite a bit in this chapter. But anything of which copies are made would do. We may suspect that the first replicators on the primitive Earth were not DNA molecules. It is unlikely that a fully fledged DNA molecule would spring into existence without the aid of other molecules that normally exist only in living cells. He says that the first replicators were probably cruder and simpler than DNA. Then he continues, there are two other necessary ingredients which will normally arise automatically from the first ingredient, self-replication itself. There must be occasional errors in the self-copying, ingredients for evolution by natural selection. Even the DNA system very occasionally makes mistakes, and it seems likely that the first replicators on Earth were much more erratic. And at least some of the replicators should exert what he calls power over their future. And this is his reference to power. He says this last ingredient, that is power, sounds more sinister than it actually is. All it means is that some properties of the replicators should have an influence over their probability of being replicated. At least in rudimentary form, this is likely to be an inevitable consequence of the basic facts of self-replication itself. So power, then, is the ability of a replicator to have an influence over the probability that that replicator will be copied or replicated. Think of it as the power of genes. Genes are the replicators in biological life as we know it. So power, the ability of the gene to influence its ability to get transmitted to future generations. Okay, that's the very special sense in which we're talking about power.
Okay. Yeah, I think that makes sense. Because I also was a little, I felt hazy on exactly how he was defining power in this chapter, but I think that that's a helpful way to put it.
Yeah, and there are. I'm going to skip through some of this and just point out sort of the thread of his argument here with regard to the power of replicators to influence their ability to get transmitted into the next generation. So he goes on to say, this is on page 184, the first replicators probably were relatively crude, low fidelity contraptions in comparison to modern DNA, replication machinery, modern DNA. The first replicators were probably incredibly simple, and the power, such as they had to influence their ability to get transmitted to the next generation, was probably fairly weak. But all that matters is that it was more powerful than alternative replicators. So on the following page, on 185, he says, this is about in the middle of the page, he says, to return to our primeval replicators, some of the simplest ones that initially existed. You can't just go straight from no replicators to genes and DNA, because DNA is incredibly complex. So to return to our primeval replicators, while most miscopyings probably resulted in diminished copying effectiveness or total loss of the self-copying property, a few, very few, and that's all you need, a few might actually have turned out to be better at self-replication than the parent replicator that gave rise to them. What does better mean? He says, ultimately, it means more efficient at self-replication. But what might this mean? This brings us to our third ingredient. Okay, I refer to this as power. Okay, I refer to this as power, and you'll see why in a moment. So again, this is the ability of a replicator to leverage itself into the next generation, basically. So moving back, starting at the beginning of the chapter then, I wanted to just jump into what he means by power. But if we look at the beginning, he opens with, I think, a really nice example. I think a very memorable example or metaphor for DNA. He says, I'm not going to read this whole example, but I wanted to just point it out and direct you to it. He opens by saying, it's raining DNA outside. And he's referring to the cotton wool that's floating down from trees, which actually each element of wool actually holds inside of it a seed, and in that seed are the genes, okay, that include the instructions for, or that are the instructions for building another willow tree. So he says the whole performance, the cotton wool, the catkins, the tree and all, is in aid of one thing and one thing only: the spreading of DNA around the countryside. And that's the sense in which it's raining DNA, okay, rather than raining cotton wool. Okay, the cotton wool is incidental. It's used to leverage DNA into future generations.
Right. So, and that's sort of at large what he's talking about in this chapter when he talks about power is just the adaptations that organisms use to, like you said, leverage their DNA into the next generation.
Yeah, and just continuing with this, this particular, theme. So, we've been talking about power and archives. His reference to archives is in general, or with broad brushstroke, referring to the fact that the archives are the information. The archives are the instructions for building more replicators. In this case, the genes that themselves build. The genes are the replicators. The genes provide the information that builds the phenotype. That is, that builds the body. Okay, or in this case, the tree and the cotton wool, but all of it is in service of leveraging into the next generation. Okay, the genes that provide those instructions, the archive of information that produces those willow seeds. Not because they want to. I mean, genes are just information. They don't want to be copied. But the nature of life and the nature of evolution by natural selection is such that the genes that exist today, by definition, are those genes that were more successful at replicating themselves, at getting copies of themselves leveraged into future generations. And all that matters is it's not that they're perfectly powerful. It's that they're more powerful at doing so, okay, than alternative genes.
Right.
So that's the broad brushstroke of what he's talking about in this chapter. Now, he does importantly point out that, in terms of life on Earth, and in terms of DNA and the genes that code for or build the phenotypes that are then used to leverage copies of those very same genes into future generations, these are bits of digitized information, basically. A gene is either there or it's not there. Okay, you don't get pieces of genes, or, I mean, not literally. You don't, information, contrary to Darwin's thinking, inheritance in biological life on Earth, inheritance is particulate. Inheritance is, another way of saying particulate is digital. Zeros and ones. The gene is either passed on or it is not. And when you have sexually reproducing species, you've got males and females. Each individual has a full complement of genes relevant to that species. But when those two species produce offspring, each offspring inherits one half of the genotype from one parent and one half from the other parent. And they combine to form a full genotype. So either at each locus on a chromosome, an organism either gets the gene from the father or from the mother. Okay? With the result that inheritance is not blending, as Darwin once thought, with, much as paint, with paint, you mix, white and red, you get pink. That would be a blending sort of inheritance, where there's a blending together. In this case, it's particulate inheritance. Either you receive the gene or you do not. And either it comes from the parent, the father, or the mother. And Darwin was not aware of this, despite the fact that Gregor Mendel, a scholar monk, who is most famous for his pea plant experiments, he provided some of the first evidence that inheritance is particulate rather than blending. Seeds are either wrinkled or they're not wrinkled. They're either wrinkled or smooth. They're not sort of wrinkled or sort of smooth. Okay, they're one or the other. This is important because Darwin himself recognized that blending inheritance, the idea that that in each generation there's a blending together. He recognized, despite the fact that he didn't have an alternative explanation, he recognized that this would very quickly sort of water down, complex machinery to the extent that you were blending together, traits from one organism and another. It would seem, at least in principle, to sort of water things down, which he knew wasn't the case, but he didn't have a better explanation. He recognized at the time that the great weakness in his theory was a failure to provide a workable theory of inheritance or heritability. He pointed it out, and he was, his critics were appropriately, critical of this problem with his theory about how does this work? Because if you blend things together over generations, you're going to get a big mess. He knew that's how he couldn't work like that, but he did not know how. That was the contribution of Gregor Mendel, although that didn't come until the 1930s, where people sort of rediscovered Mendel's work and integrated or synthesized Mendelian genetics, particulate inheritance, with Darwin's theory of evolution by natural selection, the consequence of which is what's often referred to as the new synthesis. This is Darwin's theory of evolution by natural selection now with a workable theory of inheritance or heritability, particulate inheritance.
And I think in around the same part of the chapter, Dawkins does explain the appearance of blending as being, the attempt of multiple genes to assert their effect over the same locus. So if that's, seems confusing to anyone because and that's probably where a lot of Darwin's difficulty came in, I would imagine, is that, there is so much appearance of blending in certain traits like fur color.
That's right.
But, as Dawkins explains here, like I said, that's just the influence of multiple sort of contrasting or differing genes or, DNA information from the mother and the father trying to assert their control over the particular, like you said, the particular locus for fur color or whatever trait that may be. So.
Yeah, absolutely. And so, right, there's the illusion of blending. There's the illusion of blending inheritance with some traits, but not with others. And it's that illusion that sent people during Darwin's time astray, sort of struggling to understand how the stuff from mothers and fathers come together to produce, a whole offspring. One of the things, there's a section I want to jump to. There's a couple of additional points I think that are worth highlighting. And the first one of which is on page 180. And he's gone through the various features of DNA and DNA molecules and the fact that DNA molecules represent a form of information technology, digital technology. Okay. And he says, this is in the middle of page 180. So he reminds the reader that we've seen that DNA molecules are the center of a spectacular information technology. They are capable of packing an immense amount of precise digital information into a very small space. Okay? And they are capable of preserving this information with astonishingly few errors, but still with some errors, for a very long time, measured in millions of years. So he asks, so where are these facts leading us? What are we doing here? He says they're leading us in the direction of a central truth about life on Earth. The truth that I alluded to in my opening paragraph about willow seeds. This is that living organisms exist, and this is really important. Living organisms exist for the benefit of DNA, rather than the other way around. And he says this won't be obvious yet, but he hopes to persuade you, the reader, of it. The messages that DNA molecules contain are all but eternal when seen against the timescale of individual lifetimes. The lifetimes of DNA messages, give or take a few mutations, are measured in units ranging from millions of years to hundreds of millions of years, or in other words, ranging from 10,000 individual lifetimes to a trillion individual lifetimes. And he says, each individual organism should be seen as a temporary vehicle, okay, in which DNA messages spend a tiny fraction of their geological lifetime. That is a really important metaphor or a really important idea to appreciate, is that individual organisms, okay, individual trees, individual humans, including me, including Gavin, including you guys, individual bodies are the temporary vehicles for the genes that built them. They built them in an effort to leverage themselves into the next generation. Why are they doing that? Because that's what genes do. There is no purpose, there's no goal, okay, there's no long-term sort of plan. The genes that exist today and build individual organisms exist today because they were relatively successful at getting themselves copied. That is, at getting themselves into situations where they were part of, a collection of genes building an organism that could then go on to survive and reproduce and then transmit those genes into yet another generation.
Yeah, that I like that explanation, and while you were saying that, it kind of made me realize that, and in a lot of ways, this feels like sort of the culmination of a lot of the things he's been talking about in the
That's right.
chapters leading up to this, in the sense that, one thing I'm sure the students have noticed while reading this so far is that Dawkins talks a lot about, and he spends a lot of time trying to distinguish between what's happening in natural selection and the kind of natural physical properties that create weather or create natural rock formations or whatever. And what he is approaching in these two chapters, in 5 and 6, to me feels very much like, he's getting very close to the natural physical properties that created the first self-replicators, and in a way, how the first self-replicators were really not much more than other natural physical chemical processes. But after the initial replicators started to evolve more complicated ways and more efficient ways of replicating themselves, and through natural selection, the best designs, the best models of these were the ones that survived and continued to reproduce, and eventually made, one way of saying it, is more and more complicated or more and more convoluted ways of getting, like, replicating to the point where, at one end you have replicators literally just making more of themselves in kind of like a ball of, DNA or RNA or whatever prototype you want to imagine,
Right.
to making cells that encapsulate them, to copy themselves and make DNA, to making multicellular organisms that sexually reproduce in order to pass on and replicate DNA, but all to the effect of, replicating, or replicating the DNA. Like, as you said, DNA, or the replicator, is the only really immortal part of the organism. The rest is just a vessel, a temporary sort of mechanism or machine to sort of catapult it from one body into the next. So
Absolutely, and you're right. That is where he's leading with this chapter. I mean, what he's going to be doing here, and what he is doing, is explaining or making the case for, this, that DNA and the DNA replication, machinery in particular is extremely complex as we see it today. The process by which genes, as bits of information, leverage themselves into future generations is, in fact, based on wonderfully evolved machinery. And so what he's leading to at the end of this chapter is, but how did that get there? How did that evolved machinery get there? It can't be, or it's extraordinarily unlikely to be the case that DNA, for that matter, that genes, sort of poofed into existence, because they are already themselves complex elements that rely on complex machinery to get themselves catapulted, as you say, into the next generation. So towards the end of this chapter, The Power in the Archives, he lets loose that question of, but where did this come from? Okay, the machinery and the genes themselves, okay, the replicators themselves and the replicating machinery. Again, it can't just poof into existence, already complex, any more than, the human eye can poof into existence, already complex. So before we get there, let me just summarize a couple of further points. This is on page 192, towards the middle of the page. He says, the end of the first full paragraph, he says, therefore, the DNA itself exerts an influence over its own replication via the attributes of bodies. Okay? Hands, eyes, hearts, and so forth. DNA can be said to exert power over its own future, and bodies and their organs and behavior patterns are the instruments of that power. Okay? Then he goes on, and he makes reference to, he makes some initial reference to beavers and dam building in beavers. And if you're going to hear more about this, or maybe we don't in the next chapter, but he's using this as an example of what kinds of changes, okay, genes have that can exert power or an influence on the likelihood that that gene in and of itself is transmitted into a future generation. And towards the end of page 193, he says a subtle alteration in the wiring diagram of a particular part of the beaver's behavior has occurred with this single change in gene, a single mutation. The indirect, indeed far removed consequence of a change in the DNA tag. So he takes you through a series of steps by which a single genetic mutation, through a cascading series of consequences, causes a beaver, for example, to keep its head a little bit higher above water as it's swimming with its log to put into the side of its, to continue building its dam. He says, again, moving through a lot of this example, just trying to get to the meat of it, he says on page, increased stickiness of the logs, the fact that it's a little more muddy, having been held up above the water. The increased stickiness of the logs is a consequence, again, a very indirect consequence of an alteration in the DNA text. Okay? It's a heritable consequence of an alteration in a gene, okay? A mutation that has, through a series of, tortuous, perhaps, links, has the effect of producing a more sticky, log that's being carried, and therefore is more likely to remain settled in the dam, and therefore to produce a larger, lake, and therefore, as a consequence, the beaver is more likely to survive and reproduce, and pass the very same genes along that coded for that change through that cascading series of links.
Sorry,
yeah, go ahead.
No, I think that is a helpful way to sort of conceptualize what, what he's talking about with power, but also the point he's making about, genes being the focal point, and if, not that this reading is required, but reading these two chapters just makes me think if any of the students are interested in this concept and, think that idea is really interesting or they want to read more about it, I would definitely recommend reading The Selfish Gene, because,
Sure.
although his other books do a great job explaining different aspects of natural selection, I haven't really found that any of his books do as good of a job or focus as specifically on that aspect of natural selection, that, genes are sort of running the show.
Yeah.
And the animal bodies that they create are sort of extensions of them.
Right. And that was, I agree. I mean, The Selfish Gene is a wonderful book. I think it's a little more technical,
Mm-hmm.
a little technical than the current book, which is why I've used The Selfish Gene for this class before, in place of the Blind Watchmaker. But I think you're right. I think in many ways, The Selfish Gene takes these two chapters and expands them into book form.
Mm-hmm.
And it's and it's incredibly useful. But again, part of what we want to do with this class is to try to slightly wider net, I suppose, and in particular tackle the notion that Darwin's theory of evolution by natural selection actually provides a workable alternative to any theory of design. Part of what Dawkins is doing in this book is making Darwin's case that one need not postulate a designer to account for apparent design on Earth or anywhere else in the universe. So that is the sense in which I like this book, because it does sort of cast a slightly wider net. But I think you're absolutely right that his book, The Selfish Gene, really drills down to this distinction between genes or replicators and bodies or vehicles for those genes. And incidentally, the extended phenotype, which is another one of his books, really digs in to this notion of sort of the downstream consequences of genes, not just in terms of building bodies, but in terms of having effects outside of the bodies that carry those genes. So that's also a more technical, a little more difficult book. But it's, I think it's, once you have this book behind you, I think you're in a better spot to jump into the selfish gene and the extended phenotype and some of his other books. I think he's written, 15 or 16 of them, it seems.
Right.
So I want to close out this chapter here by highlighting sort of the way Dawkins closes it out. And he says, okay, so he's gone through this example with the beaver, the change in the mutation that causes logs to become more sticky and so forth. And so he makes the case that dam building, in fact, is heritable, and dam building is a phenotypic consequence of the genes that build the beaver, right? And so he says, the fact that this particular story is hypothetical, this is at the end of page 194, and that the details may be wrong is irrelevant, okay? Why is that? Well, the beaver dam evolved by natural selection, and therefore what happened cannot be very different, except in practical details from the story that he's just told. You will notice, he says, that in this hypothetical story, there were no fewer than 11 links in the causal change linking altered gene to improve survival. Okay, in real life, there may be more. Okay, every one of those links, whether it is an effect on the chemistry inside a cell, a later effect on how brain cells wire themselves together, or an even later effect on behavior, or a final effect on lake size. Okay, any of these, they're all regarded as caused by a change in the DNA. It wouldn't have mattered if there were 111 links, he says. And then finally, he says, any effect that a change in a gene has on its own replication, what he would call power, is fair game for natural selection. It is all perfectly simple and delightfully automatic and unpremeditated. Okay, something like it is well nigh inevitable once the fundamental ingredients of cumulative selection, that is replication, error, and power, once those ingredients have come into existence in the first place. That then leads to this question. But how did this happen? How did they come into existence on Earth before life was there? We shall see how this difficult question might be answered in the next chapter. So here, in chapter 6, Origins and Miracles, he's addressing even before you get to modern genes and their leveraging themselves into future generations by use of the building of phenotypes of bodies and the effects that they may have on, for example, dam building. Roll it back. What are the first replicators likely to have been? They're not likely to have been the genes that we recognize today. And the system of replication is not likely by a magnitude of 1,000 to be something as complex as the DNA replicating machinery, self-correct, error-correcting machinery that's highly accurate, and while subject to some error, very, very few errors creep in. So what he's talking about in this chapter then is how we got to that point. Okay, and he says, he opens by saying, chance, luck, coincidence, miracle. One of the main topics of this chapter is miracles and what we mean by them. My thesis, he says, will be that events that we commonly call miracles are not supernatural, but are part of a spectrum of more or less improbable natural events. A miracle, in other words, if it occurs at all, is a tremendous stroke of luck. Okay? Events don't fall neatly into natural events versus miracles. And he goes on to say on page 198, cumulative selection is the key. Okay, but it had to get started. And that's really what we're doing here. And we cannot escape the need to postulate a single-step chance event in the origin of cumulative selection itself. But that single step can't have been something impossibly complex. Okay? let me just finish this thought here. On the next page, he says, but if replication needs complex machinery, he says, well, let me back up to the first sentence in that example. He says, the theory of the blind watchmaker, that is the theory of Darwin's theory of evolution by natural selection, the theory of the blind watchmaker is extremely powerful, given that we are allowed to assume replication and hence cumulative selection. But if replication needs complex machinery, since the only way we know for complex machinery ultimately to come into existence is cumulative selection, we have a problem. Right? There's got to be some beginning point, some simple process of replication.
Right.
Okay?
Right. Something that could have, occurred within a reasonable amount of or degree of probability.
That's right. Okay. So continuing this example, because I think it's so clearly laid out here, the issue, the apparent, the illusion of a devastating problem here. The issue that Dawkins is struggling with and that he's presenting to you, the reader. He says on page 200, some people see this as a fundamental flaw in the whole theory of the blind watchmaker. They see it as the ultimate proof that there must originally have been a designer. Not a blind watchmaker, but a far-sighted supernatural watchmaker. Maybe, it is argued, the creator does not control the day-to-day succession of evolutionary events. Maybe he did not frame the tiger and the lamb. Maybe he did not make a tree, but he did set up the original machinery of replication and replicator power. The original machinery of DNA and protein that made cumulative selection and hence all evolution possible. But then Dawkins goes on to say this is a transparently feeble argument. Indeed, it is obviously self-defeating. Organized complexity is the thing we are having difficulty explaining. Once we are allowed to simply to postulate organized complexity, if only the organized complexity of the DNA protein replicating engine, it is relatively easy to invoke it as a generator of yet more organized complexity. That indeed is what most of this book is about. And then he says, but of course, any God capable of intelligently designing something as complex as the DNA protein replicating machine must have been at least as complex and organized as that machine itself. Far more so if we suppose him additionally capable of such advanced functions as listening to prayers and forgiving sins. Then he says, to explain the origin of the DNA protein machine by invoking a supernatural designer is to explain precisely nothing, for it leaves unexplained the origin of the designer. You have to say something like, God was always there. And if you allow yourself that kind of lazy way out, you might as well say, DNA was always there, or life was always there, and be done with it. Right, I think that's a very powerful description of what's at hand here. We need a simple pseudo-replicating machinery, okay, or some means by which single-step selection can get us started on the path to complex replicating machinery. And we can't simply declare by fiat that, well, the replicating machinery is already there. It's already complexly in existence, okay? That won't work probabilistically. And again, that's the very thing you're trying to explain, is how did the complex machinery get there? And if you're just poofing it into existence, okay, whether by the use of a God or not, let's imagine you use God. Well, God did it. Okay, well, God's got to be at least as complicated as the very complex machinery that you're proposing he poofed into existence.
Right.
And so the person you're talking with could say, okay, fine, but how did God get there? Okay, and then most people who are religious will say, well, he's always been there. God is, was, and ever will be. I hope you can see that that's not an explanation. That's just declaring by fiat, with reference to a holy book, for example, that is the explanation. Take it or leave it. And that's not the way science moves forward. You can't just demand that somebody take it or leave it. You have to provide an explanation that gives the person you're talking with an opportunity to appreciate the assumptions you're making. You have to provide the evidence, basically. So
Yeah. Yep.
there we are. Got to have some means of accounting for the evolution of the the replicators and the replicating machinery.
And so, did we want to talk about, I guess, his setup for this chapter seemed sort of, setting up odds and probabilities and using that as a starting point for, what we mean by a miracle, or what he's talking about when he means that an event is likely versus unlikely, and how much chance we should allow ourselves, for this sort of first replicator.
Well, I mean, are you talking about? I was thinking. I mean, one of the things that Dawkins does in this chapter is he gives ultimately what he's talking about is the origin of life, basically the origin of self-replication. Now, Darwin's theory of evolution by natural selection presumes life exists, and then from there, Darwin accounts for the evolution of life over vast periods of time. What we're talking about in this chapter is the origin of life, the origin of the first self-replicating element or molecule. Mm-hmm. And I just wanted to point out that in each of his many books, when it's relevant for him to discuss the origin or the possible origins of life, Dawkins gives a different theoretical explanation. The truth is, we don't know. We don't know. And there's no shame in saying we don't know how life or self-replication originated. But there are multiple, more or less compelling theories of the origin of life. This is a whole field. There's a whole field of biology dedicated to this, referred to as abiogenesis. Okay, this is the production of the evolution of life from non-life, or replication, self-replication from non-self-replicating material. Dawkins gives one example of how this might have occurred, okay, relying on Carn Smith's clay molecules, I believe is the example he gives in this book. I don't want students to get buried in the particular example that Dawkins lays out, because that's not really the point. The point is, it's far too soon to give up on a workable theory of the origin of self-replication, the origin of life. There is an explanation. In fact, there are multiple explanations which are competing. In my sense is this will be, resolved. The origin of the first self-replicating molecules. We need not rely on a designer, okay, to poof those self-replicating molecules into existence. And that's really what Dawkins is attempting to communicate in this chapter. And you're right, Gavin, he does address issues of, chance and probability and how much luck do we have to play with. And I'm happy to discuss that to the extent that you think it might be helpful for students.
Well, I mean, I think it can be summarized pretty well, because he does belabor the point a little bit, ultimately to come to the conclusion that we really don't need that much chance at all, given what we know about, the physical properties of, organic molecules and chemistry as it exists on Earth, and especially as we think it probably existed at the origin of life on Earth, which would have been relatively different from, what our planet looks like now. So keeping that in mind, he kind of, I can't remember exactly the range he does. I think it's between rolling double sixes on a pair of dice and being dealt a perfect hand in bridge, and basically asserting that the chance instance for life, or a very basic self-replicator to sort of spontaneously occur, exists somewhere within that continuum of probability, and that it is really, given the time span in which we're working with, which I think he said was about 1.5 billion years, that had to occur pretty much just once, is really not that big of a chance at all.
At least once, in the sense that, and if only once, well, it has to be here, because here we are talking about it.
Right.
But it may well be true that there are billions of of Earth-like planets, okay, on which life may have evolved, okay, the vast majority of which, we could say very little about. We have indirect evidence that of such planets, okay, and therefore many scholars argue that it's unlikely that Earth is only the single, place where life has evolved. All of which is to say, it's true that we need to have some available luck, okay, some chance, okay, to get the first simple self-replicating molecule going, okay? But there is so much time to work with, okay? Just on Earth, again, 1 billion years. But if you look more broadly, the universe itself, 14 billion years. You've got so much time and so many potential locations, okay, on which this might have occurred. But the argument is it's not all that improbable, given the amount of time and given the number of potential locations or would-be Earths. Okay? So we need not throw up our hands and say, well, God did it. There may yet be plenty of luck to go around to get this process started. He might be wrong, and there may well be, a God, and it may be Yahweh, it may be the Christian God. Okay, but we don't have to go there yet. We don't yet have to conclude that any more than we have to conclude that it was the Hindu gods that did it, or that it was, the Muslim God that did it. Okay, we simply aren't at that point yet. The amount of luck that needs to be postulated is not insurmountable, okay, given the time we have to work with and given the available materials and locations.
Yes, right. I like that summarization of this chapter. Sort of the big idea is that it's just not as improbable as a lot of people might think that it is, or might think, given what they know about, or what they don't know about the time scale, which he reiterates in this chapter, is really hard to conceptualize, and like you said, the material that there was to work with, and the state of Earth at the time life would have originated. So
that's right. So he concludes by saying on page 237, we still don't know exactly how natural selection began on Earth. This chapter has had the modest aim of explaining only the kind of way in which it must have happened. Okay, the present lack of a definitely accepted account of the origin of life should certainly not be taken as a stumbling block for the whole Darwinian worldview, as it occasionally, probably with wishful thinking, is. The earlier chapters have disposed of other alleged stumbling blocks, and the next chapter, which is where we'll head next week, takes up yet another one, the idea that natural selection can only destroy, never construct. This is also, as he mentions here, this is one of the would-be criticisms of natural selection, is that because it relies on differential death, natural selection can only destroy. It can never create anything. Natural selection could not possibly build something as complex as an eye, because all it can do is differentially inflict death. All it can do is destroy or destruct rather than construct. And that's simply not true, as Dawkins will get at in the next chapter. Okay, well, this is a heady couple of chapters, and some of the applications are a little more straightforward in the next few chapters. But it's an important couple of chapters for, sort of clearing the way for really appreciating evolution by natural selection and appreciating the digital technology by which information in the form of genes leverages itself into future generations in the form of bodies, temporary vehicles for the genes that build them. And they build them not because they want to, not because they're motivated to, but because that's what they do. The genes that exist today are those that were successful, okay, at building the bodies that were more likely to survive and reproduce in previous generations. Okay, so the genes that exist today are the genes that worked.
Yeah, no, that's a good way to put it. I don't have anything else to add. You summed it up pretty well.
Okay, good. So next time then we'll talk about chapters 7 and 8, constructive evolution, and then chapter 8, explosions and spirals. So this week, again, we're asking you to watch the first 2 parts of The Genius of Charles Darwin. I think you'll enjoy them. I think you'll appreciate them. Again, you'll hear many of the same concepts in the context of different examples and certainly in a different medium from your author and from others that Dawkins interviews, and some of the other, and some really neat footage, cinematography, addressing a wide range of animals. So we'll hope that you find them as useful as we have. And we will see you then again next week. So.
All right, sounds good.